So the first derivative test, this is going to be the most common method for finding any kind of extrema. Now, I will say that what we're going to be referring to here are the relative extrema. There's more work if we want to use this test to find absolute extrema, but that's going to be one where I'm going to kind of wait and do that in person rather than through a video. So to find relative extrema, the first derivative test is the most common method we're going to use. The candidates test is not useful because the candidates test is specifically for absolute extrema, but relative extrema are more useful to us. So the benefit of this is the first derivative test will always find every relative extreme value over any function, regardless of if it's continuous, if it's an open interval or a closed interval, whether we have discontinuities, whether we have places where the function is not differentiable. The first derivative test always finds every extreme value, no matter what. Drawback, it requires the most work. And that's kind of how this works with these different tests. The faster the test is and the less work it requires, the more places where it's not, the more scenarios where that test won't work. The more stringent the test is in catching every extreme value, the more work it's going to require. So the process of this is we want to find where the function is derivative or zero, the critical points. We want to make a sign chart of the endpoints and critical points for this first derivative, which will allow us to see where the function is increasing or decreasing. If the function changes from increasing to decreasing, meaning the first derivative is changing from positive to negative, we have a relative max. If the function changes from decreasing to increasing, meaning the first derivative changes from negative to positive, we have a relative minimum. Endpoints get a little complicated with this, but I'll also admit endpoints don't come up very often with the relative extrema, but we will do examples so you get used to it. So an example of this. I have the function 3x to the fifth minus 4x cubed minus 3x. And I want to find all of the relative extrema and identify are they maxes or mins. Well, I'm not told a domain, and polynomial means that my domain is all real numbers. That's really nice for us because it means there are no endpoints. I don't have them complicating. I don't have the endpoints complicating things for me. So I'm going to move on to my critical points. For my critical points, I need the derivative, first derivative, which will be 15x to the fourth minus 12x squared minus 3. Because I'm going to be working with this, I'm going to go ahead and try to factor this as much as I can. So if I pull a 3 out, I'll have 5x squared minus 5x to the fourth minus 4x squared minus 1. I can factor that by unfoiling. So I'll have 5x squared. There'll be an x squared here. This is minus 1. This is a plus 1. And then I can factor the x squared plus 1 even. I'll have 3 times 5x squared plus 1 times x plus 1 times x minus 1. The reason I chose to factor it is I know I'm going to have to set this equal to 0 and try to solve it. And I'm really lazy and don't feel like using my calculator. So I need to know, is this ever undefined? Well, my derivative is a polynomial, so it is never undefined. And then I need to know, where is my first derivative equal to 0? Well, 3 is never equal to 0, so that doesn't have an effect. 5x squared plus 1, the only way that equals 0 is if x is an imaginary number, and we don't work with imaginary numbers in AP Calculus, so that factor is gone. If x plus 1 is equal to 0, that means x could be negative 1. And if x minus 1 is equal to 0, that means x could equal positive 1. So I only have 2 critical points and no endpoints. So I'm going to draw a number line that references my domain. There are no endpoints, so that's why it's going on in each direction forever. I put my critical points on there. As I said, there were no endpoints. And then this is a sign chart for the first derivative, meaning I'm going to use this to decide over what intervals is my first derivative positive and over what intervals is my first derivative negative. To do this, I just pick a value in a region. So this region, sorry, hard to see there. This region, x's are less than -1. So I pick a number less than -1, like -2. If I plug that into my first derivative, I'm going to plug it into the factored part. I have a positive times a positive times a negative, which overall is going to be positive. This means that f is increasing there. Then I have the region between -1 and 1. I pick a value there, like x equals 0, plug that into my first derivative. Again, I'm going to use my factored form. I'd have a positive times a positive times a positive times a negative, which is negative, meaning that f is decreasing there. And then pick something bigger than 1 for the third region, positive times a positive times a positive times a positive. So f is increasing. So on my sign chart, some people like to do a quick little sketch on the sign chart of a function while it's going up, down, and up. Again, that's just a little sketch showing increasing, decreasing, because then this is easier to see. Oh, right here, I'm going to have a relative max. And right here is a relative min. So I can now answer the question of where are the relative extrema and what type. I have a relative max at x equals -1. I have a relative min at x equals +1. I don't need to give the function values because they don't ask me what the extrema are. They just ask where.